Well, hello and welcome back. And if you remember from before Easter, we were right up to the last lesson of this topic. You're going to be giving your assessment on Wednesday, so I highly recommend once you've watched this video, going over all the videos that you've been set so far, making sure you're very clear on what the learning objectives are, design yourself a mind map, get your revision done, pause the videos in the right places, and really make sure that you're up to speed with everything for the assessment you're going to get on Wednesday. I know you've also been given some worksheets by Miss Bladen, and obviously they're going to relate to what we're doing, so make sure they're done as well. However, learning objectives for today. Excuse me, bit of a cold. Now, two learning objectives. The first one is about using and understanding word equations. And that's something that I tend to find that people overcomplicate. They seem to make that a lot more difficult than it actually is. Sorry. And the second learning objective is to describe something called a decomposition reaction, which again is fairly straightforward and not complicated at all. So before I give you a specific chemical example for a word reaction, I'm just going to talk to you about baking a cake. If I wanted to bake a cake, I'd need some ingredients. I'd need maybe flour, I'd need sugar, I'd need egg, a bit of butter, and the product I'd make would be my cake. Okay? So how would I write that down as an equation? Well, I could just simply write flour plus butter plus sugar plus egg equals cake. And that would be a perfectly fine word equation. That is what we are doing in chemistry when we do our word equations. It's no different, it's no more difficult. So if I wanted to write a word equation for the production of water from hydrogen and oxygen, well, I know that I am starting off with hydrogen and oxygen, and I know that I am going to make water. So my word equation would just be hydrogen plus oxygen equals water. But although I've been saying equals, we don't actually use the equals sign. You can see here we have an arrow pointing from iron and sulfur to iron sulfide. Now here we've taken iron, we've reacted it with sulfur, and we've made our iron sulfide. And I want you to take notice of the words underneath those funny shaped brackets. The ingredients that you like, we call those the reactants. So if you hear the word reactants, it just means the ingredients in the chemical reaction. The product will be the final thing that's been made in the reaction. And sometimes we'll have more than one. You know, I can react together methane and oxygen to make carbon dioxide and water. My word equation will be methane plus oxygen, arrow, carbon dioxide and water. And I'd have two products from my two reactants. So it really is straightforward, and I'm sure that in the worksheets that you've been sent there'll be some practice on that for you. So let's just move on a little bit and look at what we would expect to see in a chemical reaction. So I'm going to click here, and we've got three chemical reactions. On this left chemical reaction here with the wood, we can clearly see that heat is being given off, and that is a sure sign of a chemical reaction. If we have a temperature change, you know, we mix two things together, we get a temperature change. Either that temperature goes up, meaning it's what we call an exothermic reaction, or the temperature goes down, making it what we call an endothermic reaction, but we have a change in temperature. That is a sign of a chemical reaction. Now, if we look at the eggs, that must be an endothermic reaction because we have to heat it and continually heat it to cook the eggs. But the eggs cooking themselves are definitely a chemical reaction. How do we know that? Well, what do we notice when we cook an egg? We notice a colour change. It physically looks different. We have a very, very different colour. With the egg white goes properly white as opposed to transparent. That is another sign of a chemical reaction. If we look underneath at the iron rusting, the iron has changed colour. Again, a sign of a chemical reaction. Now, what other signs are there that a chemical reaction is taking place? Well, we might have bubbles given off if we've got a gas. It might look like something is dissolving or disappearing. Now, sometimes that could be a physical change, not specific to a chemical reaction, that one. A physical change could just be putting some salt in water and it dissolves. But if you put some magnesium into some acid, it's also going to look like it's dissolving. It's not actually dissolving, it's reacting with the acid around it. But to the human eye just watching it, it looks like it's dissolving. So there's a few signs of chemical reactions there for you. Now, if we have a look at the learning objectives again, we'll notice we've not touched this second one yet on the example of a decomposition reaction. Well, a decomposition reaction we can almost imagine as being the opposite of what we spoke about so far. You know, we've spoke about, for example, iron plus sulfur becoming iron sulfide. But what if I had iron sulfide and I could split it back into the iron and sulfur just by heating it? The word decomposition you'll have heard before maybe in biology. You take an apple and you throw it in your garden and a couple of months later it's gone. It's decomposed. It's broken down. Now you'll often see the term decomposition preceded with the word thermal that you can see here. A thermal decomposition reaction is where something gets broken down, but we do it by applying heat. Okay, so we heat something, a chemical, we break it down, thermal decomposition. So what's the most famous example of this reaction that you will need to know? Well, anything in chemistry that ends in the term carbonate is going to be a likely candidate for a thermal decomposition reaction. In this example, we've got copper carbonate, but you could pretty much put the name of any metal in front of that. We could have lithium carbonate, calcium carbonate, potassium carbonate. I think you get the idea. But when we heat something that's a carbonate, one carbon atom and two oxygen atoms break off. Okay, carbonate is CO3. Okay, that's what we, so copper carbonate will be a copper atom, one carbon atom and three oxygen atoms, CuCO3. Don't worry too much about that at all. We're looking at the word equations, not the symbol equations at the minute. But if you see a carbonate, just know that if you heat it, some carbon dioxide will be given off. We will have one carbon and two oxygens break off. So if I'm heating copper carbonate, I'm going to produce carbon dioxide. If I'm heating calcium carbonate, I'm going to produce carbon dioxide. If I'm heating lithium carbonate, I'm going to produce carbon dioxide. But what's left behind? If I've got copper carbonate here and I heat it and some carbon dioxide breaks off, what is left here from the original copper carbonate? Well, we produce an oxide. So if I have copper carbonate and I heat it, carbon dioxide will move away, but what I've got left over is copper oxide. If I have lithium carbonate here and I heat it, carbon dioxide will move away, but I'm left with lithium oxide. And if I have potassium carbonate and I heat it, I'm left with potassium oxide. And it's always going to be the same in any example that you're given like that. Now, again, why is that a thermal decomposition reaction? Well, thermal because I've got to heat it to make it happen, and decomposition because that molecule is breaking down into two other things. How would I write a word equation for that? Well, here, my ingredient, the thing I'm starting with, would be copper carbonate. That is producing copper oxide and oxygen. So I would write copper carbonate, I'd have my arrow, copper oxide plus carbon dioxide. Or lithium carbonate, arrow, lithium oxide plus carbon dioxide. Or potassium carbonate, arrow, potassium oxide plus carbon dioxide. Now, if we look at the setup that you've got here, there is a tube. And this tube is going into the lime water here. Now, the tube is there to carry that carbon dioxide and pass it into the lime water. Now, if you've done respiration with your teacher, you may be aware that lime water has a special property when it's mixed with carbon dioxide. And if we look at the bottom half of this picture, we can see that the lime water, when it's mixed with carbon dioxide, is going to go white, a cloudy colour. Now, the term you're going to use for that is a precipitate. We get a white precipitate. A precipitate is a solid forming inside a liquid. And this cloudy whiteness comes because we get tiny white particles of a solid forming in the lime water when carbon dioxide passes through it. If you do geography, you may hear about a precipitate in the context of rain. But that is a liquid forming inside a gas. We have one state forming inside another, which might be an even better explanation of what a precipitate is. But in chemistry, we're almost always talking about particles of solid being produced inside a liquid. So lime water is our carbon dioxide test. If we have a gas and we want to test what it is, if we bubble it through lime water and it goes white, we know it's carbon dioxide. That's one of your gas tests. We can see that the product of this is our copper oxide, which we've already mentioned, which is a black powder compared to the green powder, which is copper carbonate. And again, that colour change is indicative of a chemical reaction. So, I think we've covered everything that you need there. I will make sure that you've got your assessment on Wednesday, and then I will do a video which I will release on Thursday, once you've had a chance to do your assessment, of me going through the assessment and giving you all the correct answers so you can self-mark, self-assess and see how you've got on. Good luck.